Hello and welcome to ML with AP. The topic for today is support vector machine. Let's learn. This is what we are going to cover. We'll start with maximal margin classifier. This is the absolute basis of SVM. Then we'll progress to soft margin classifier, which is also known as soft vector classifier. After that, we'll learn about support vector machine. After that, we'll learn something which is super important, kernel trick and the intuition behind it. We'll also go through all the maths behind support margin classifier and support vector machine. Towards the end, we are going to code everything in SciKitLearn. So hang on. I have a feeling that this video is going to be slightly longer. If that's the case, I will probably break it down into 2 or 3 videos. So if you are watching the first part of this video series, look out for the second and third part as well. Without further ado, let's jump in. First thing first, maximal margin classifier. This is the basis of support vector machine. But what it is, as the name suggests, there is a classifier word in it. So obviously it's a classification algorithm. Let's try to understand this with a small example. This is our iris dataset. What we have done is we have 2 axes. On the y-axis we have petal width. On the x-axis we have petal length. Okay, our iris versicolor is the blue squares and our green dots are the iris setosa. Okay, very clear binary classification problem based on 2 features, petal length and petal width. Now friends, you tell me, looking at this diagram on the left side, you tell me, this being a discriminative algorithm, obviously we have to identify a decision boundary. We need to classify this into 2 classes, okay? And for that, we need a linearly separable line, right? A linear line, we should separate the data. That's what classification is about. Now, let's see. We have drawn 3 lines over here. Let's take these lines one by one. Obviously, the dotted line in green is not doing a very good job because it is not able to classify the 2 classes, setosa and versicolor, properly. So we can discard that. Let's talk about the pink line. The pink line, although it is able to separate these 2 classes into 2 different groups, similarly, the red line also is able to do. So which line is better, pink or red? Or are there more lines like that? How to identify that? Let's see the picture on the right. So the picture on the right, if you see, there is a black line over here. Now the black line, friends, looks very much better. Intuitively, it looks a lot better than your green dotted line, the pink line, and the red line. Why it is so? Intuitively, if you see, or pictorially if you are seeing, then this black line is better because it is far away from any of the nearest observations, right? Both on the setosa and on the versicolor side. Correct? That's why it appears that this black line is doing a very good job of separating or very good job of being a decision boundary and separating our 2 classes. Okay? Now, friends, this is what is called maximal margin classifier. Why maximal? Maximal because you have to separate the 2 data sets with a maximum margin. So this black line over here, if you see the black line, it's separating these 2 data points with a maximum margin. And it's a classifier. That's why it is called maximal margin classifier. Okay. Let's try to see this over here. Yeah. So what is our goal for this classification? Okay. Now the goal for any classification is to classify the data correctly. That's first goal. The second, we have so many lines. Now out of all these lines, pick the line which has the greatest distance to the point, from the point closest to it. What do we mean by that? Let's see. Let's see the picture on the right. Now this black line is doing a very fine job of being a decision boundary, right? Why? Because this is one of the line which is at the greatest distance from the nearest observation of both the sides or both the classes, right? So these two observations which are there or the nearest to the black line are called support vectors. So vector is nothing but a point in a two-dimensional or multi-dimensional space. So this point and this point, since they are nearest to the line, midline, they are called support. The dotted line, the two dotted line are called the margins. So that's why it is maximal margin classifier. So we are trying to obtain a line which has the maximum distance from the nearest observation of both the classes. Okay. So friends, how intuitively we are arriving at this line? We are arriving at this central line because this is equidistant. So this distance and this distance are equidistant, right? So think it like a road, and we have to carve out a road which has the maximum width of the road, okay? And the center of the road will be our decision boundary, and the edges of the road will be our where the support vector lies or the nearest observation lies are the margins, okay? So margin are the dotted lines. The thick black line is our decision boundary. The observations which fall on the margins are our support vectors, correct? And one thing also to note is that these two distances, the margins are both on the left and the right side, or the positive or the negative class, or the versicolor or the setosa class, will be equal. So these distances are equidistant, they are equal. Okay, friends, you recall, if you have noticed, I skipped one page. Let's go back and deal with this particular thing. So maximal margin classifier, it's sensitive. A lot of machine learning algorithms are sensitive to scaling, right? Or if all the features are not on the same scale, our results or the model performance will go down, right? SVM or SVC, support vector classifier or maximal margin classifier, is also very sensitive to feature scaling. So it is always recommended to do the feature scaling before sending the data to the model. Okay, so let's see how it is. On the left side, we have unscaled data, okay, without scaling. So if you can notice, then I have two features, x1 and x2. x2 is the x-axis and x1 is the y-axis. If you can see, they have a very different scale. This is 0 to 100 and this is 0 to 6, right? In this particular case, if we have to draw a line on an unscaled, right, we have not done the feature scaling, you can think that this road which we are creating, right, is very, very narrow and thin, right? And the shape of the road also, you notice it is very horizontal in nature, right? Let's see what happens if we do the feature scaling. And we have used a standard scaler over here. A standard scaler is a package in, again, a library inside SciKitLearn. What it does is, standard scaler, this is the definition of a standard scaler. What it does is, it will mean center to 0 and our standard deviation and divide by a standard deviation. So we have unit standard deviation. That means standard deviation will become 1 and the mean will be centered to 0, because what we are doing, we are subtracting everything minus mu, right? So we are centering our mu to 0 and our standard deviation as a unit standard deviation, which is 1. Now why this name standardization or standard scaler? This is with the standard normal distribution or Gaussian distribution. If you recall, a standard normal distribution is also something where mu is 0 and our sigma is 1. So we are trying to mimic our data, or we are trying to scale our features to standard scaler or to the standard Gaussian normal distribution, right? And how we are doing this trick? The standard scaler, as I was telling, that package in SciKitLearn, effectively it is implementing this. It is calculating the mu, it is calculating the sigma of all the data points, and then it is running this formula over there, x minus mu by sigma, and whatever is the new z thing is coming or z thing is coming, that is the new z attribute. That is the new z attribute which is getting, and it has done the same thing for x1 and for x2. Once we have done the standard scaler or feature scaling, friends, now you notice the maximal margin classifier, how beautiful it is looking. The roads are wider now, right? And it is also a better fit. If you notice, now my maximal margin classifier is tilted, right? There are two support vectors on the left side and there is one support vector on the right side, right? So this is a better, this will give you a better model and a better accuracy and predictive power if you scale your features. Okay, let's move on. We have already seen that. Now, maximal margin classifier looks very good, but it suffers from two problems. Can you guess what are these problems? They are listed over here. The first problem is, if we have an outlier, let's say, so there is this green circles, these were setosa and the squares were versicolor. Let's say if we have one observation which is falling over here, it is clearly an outlier, but can our maximal margin classifier do a job of linearly separating these two classes? Maximal margin classifier is a linear decision boundary, right? There is no way we can put a linear decision boundary and separate these two data sets cleanly also. No matter how hard we try, we'll not be able to do, right? Because this is deep within over here. So that is the first problem, that it doesn't scale well to the outliers. One outlier and this algorithm fails. What is the second problem? Now the second problem, if you see, in this particular case, the outlier is not over here. The outlier has only go all the way till here, right? Over here. But what happened to our decision boundaries? Instead of a thick black line over here, our decision boundary has shrunk, or the road had shrunk to a very small thickness, right? If you notice, if you recall, the thickness was very, see, the thickness was so much over here, right? But if you do it over here, if one data points move, then maximal margin classifier has to accommodate this data point which is actually an outlier as a support vector. And to do that, it has to make the road very narrow, right? So the two dotted lines, if you see, it has become very narrow, right? So in this particular case, it will work, but the new value which will come, it will not be able to generalize it well. Why? Let's say the green square, one green square will come over here, which is very near to the other versicolors, right? But our classifier will try to mark it as setosa, not as the green, but not as the squares, but as the circles, right? Because it will come on the left side of the road, right? So there are two problems. One is that it is very sensitive to outliers, and second is the less generalization. It is very hard classifier. You cannot generalize well. Another way to see that is with the example on the left side, right? Just ignore the small c and large c for now. Okay, we'll deal with that just in a minute. But let's say we have again two classes. The green straight line was our original decision boundary, right? We have seen one observation of triangle towards the left over here. Our decision boundary will move from this vertical line to a very slanting line over there, right? So such a huge shift in the decision boundary because of what? Only one data point, which is probably an outlier, which has gone. So friends, I hope this makes sense, that what is the problem or main issues with the maximal margin classifier, right? Let's see how to overcome that. Okay, now we know the problem is there. What is the solution? The solution is soft margin classifier. What we are dealing till now was hard margin classifier or maximal margin. Hard means it was not accommodating anything inside the width of the road, right? Our support vector were very hard boundaries for that road, right? Now in this particular case, in the soft margin classifier, what we'll do is we'll do two things. One is we'll allow violations. What do you mean by allowing violations? Allowing violations, that it's okay if something is misclassified also. But what we'll gain if we allow misclassification, we'll gain on generalization. Our predictive power for the unobserved or unseen data will be better. Let's see it with an example. Let's see if we have a maximal margin classifier like this, very hard. So we have these support vectors, this red dot, and this blue dot over here, support vector, and this margin is very, very thin, right? Over here, very thin, very strict, hard margin. Let's say, what if we allow violations to happen? If we allow violations, this one violations to okay, if it's okay if we misclassify this one thing, what will happen instead? We can actually draw or classifier or the decision boundary in a much thicker boundary, right? Or much thicker road. Rather than having a very narrow road, we can draw a very thick road by allowing one misclassification. Now, if you notice, our support vector is this and this, right? These are the two support vectors, and our road has become thicker. So any new observation which will come, there are more chances or more likelihood that it will be classified properly because we are allowing misclassification, and by that we are improving the generalization. Okay, so it will generalize better on the newer unseen data. Let's try to see it with one more example, and please ignore the C for the time being. We'll just come in a minute. Okay, I've been telling you that ignore C, but we'll see what this C is. Okay, let's see the first example. Okay, the first example over here, if you see, the road is very, very thick, right? But we are allowing lot of data points to be misclassified also and to come on the road also, right? There are a lot of data points of both red and green which are there on the center of the road or towards the center of the road, right? But according to your maximal margin classifier, everything should be outside the road. The first data point is the support vector, right? But in case of soft margin classifier, we allow these things. Okay. Now let's take another case over here. We allow little bit less misclassification, little bit less data points on the road. Our road will become thinner, right? It will become further thin. Okay. If we keep on doing this, it will become further thin, right? So the road thickness and how much we allow misclassification are inversely proportional in the relation, right? You got that? Okay. So what we are doing with soft margin classifier, we are allowing violations to gain what? To gain better generalization for future predictions, right? So friends, till now we have seen maximal margin classifier. We have also seen soft margin classifier. Okay, where we are allowing misclassifications to happen to gain generalization so that our prediction power is improved, right? Now, one thing which we have not dealt till now or we are missing is the calculation of the cost or the loss function. Since this is a classification algorithm, any machine learning algorithm will have an objective function which needs to be maximized, or it will have a loss or a cost function which needs to be minimized. So what is the loss or cost function in case of support vector classifier or maximal margin classifier? Let's see that. To see that, we have to understand a basic concept which is called cosine similarity. Let's first understand cosine similarity. Okay, so to understand cosine similarity, let's assume that we have on our Cartesian plane, we have 2 points, right? We have B, A vector and B vector. Obviously, it will be like this is A vector and this is B vector, and the angle between them is theta, right? Now, there is something called dot product, if you know, or the inner product as it is called. So dot product of A dot B is defined as the projection of A onto B. Like you have to draw a perpendicular line from A to B. What it will be? In case of trigonometry, if you know, this will be norm of A, right? This is just the scalar quantity, the length of A, right? and this vector is defined because it has a direction also. Okay, so A dot B or A dot product B will be equal to norm A norm B into cos theta, right? This is what it will be. And what will be this projection? This particular length will be nothing but your norm A, which is the length of the vector A, into cos theta, right? So this base will be norm A cos theta. Now, why dot product is called a similarity measure, right? Let's understand that. So when we say dot product, what it gives you a scalar quantity, right? A dot B, or the dot product of two vectors, is a scalar quantity. It tells you about the length of A, length of B into cos theta, 3 component. This is the length, a scalar quantity. This is also the length, a scalar quantity. This cos theta will determine whether how much similar they are. And how it is determining that cos theta, if you know, if the two vectors are going both in the same direction, cos 0 will be 1, right? So they are most similar. That means they are actually going in the same direction, right? But if they are opposite direction or they are different means they are going perpendicular or in the opposite direction, this particular scalar quantity will become smaller and smaller. And the way to see that will be, let's say this same length A is over here, right? This particular projection will become bigger. If the same quantity, if the same A is, let's say, tilted little bit higher, same height, same length, norm A is actually the same. If we do the projection now, what will be the length? The length of the projection, A cos theta. Norm A cos theta will be smaller. That means this particular vector is less similar to B than this particular vector. So this A, and let's say this is A prime. So A prime B are less similar than A and B. This is the whole concept of cosine similarity. Okay, and cosine similarity is measured like this: A dot B, which is norm A norm B, the length of A length of B, multiplied by cos theta, right? And this concept will be using in case of our math behind our maximal margin classifier and soft margin classifier. So let's see that. Okay, so to understand the maths, let's again draw our, okay, and let's say we have few data points over here, something like this and this, and we have some different class also. One is this, and we have to do a decision boundary, right? We have to fit a maximal margin classifier, a soft margin classifier, right? What we'll do over here, friends, what we'll do is that these two will be our support vector, let's say. So I will draw the margins first, and then my decision boundary will be in between, right? These two distance will be equidistant, right? Just assume that these are equidistant. Okay, now suppose we have to do the projection or the prediction for a new data point which has come. Now how we will do the prediction for the new data point? Let's say my new data point has come somewhere over here. Okay, this is my new data point. Okay, how we'll do the projection? What we'll do is we'll assume a vector W of unknown length. We do not know what is the length of this vector W, right? But all we know is this is perpendicular to margins and the perpendicular to our decision line also, the midpoint. So it's perpendicular to the edges and to the middle of the road also. Correct? Now what we'll do is, let's say this point is X, for which we have to do the prediction. What we'll do? This is my X vector, right? This will be a vector, X vector, right? We'll take the projection of X onto W. Okay, we'll take the projection of X onto W. Okay, correct? And how we'll write it? We can write just how we learned the dot product or the cosine similarity is W dot X dot. and we'll mark this quantity as greater than a constant c. Now we'll just see that why we are marking it as a constant c, right? Now think, friends, over here, what we are trying to do over here is we are trying to project any new point or new observation for which we are trying to do a prediction onto a vector which is perpendicular to our decision lines, okay, or decision boundaries. Why we are doing? If we do the projection of this, then we are getting a cosine similarity of this. What we are getting? We are getting this particular length. So we are trying to assess if this length is greater than a fixed constant, then let's say this side was a negative class and this side is positive class, okay? The blue ones are the positive, the pink ones are the negative. If it is higher than a particular threshold, which is denoted by C, then I should, if my dot product is higher than a particular threshold, I should categorize this as a positive class. If it is lesser than a particular threshold, I should categorize this as a negative class. So suppose intuitively, if you see this particular observation is somewhere over here, what I will do? Now this class and the projection will be this. In this particular case, my dot product of this will be this particular quantity, very high, very big line, right? So it will cross my threshold. And what is my threshold? My threshold is this, my decision boundary. If it crosses my decision boundary, I should say that it's a positive class, right? Simple. This is the basic understanding. Now let's do little maneuvering also, little mathematical. So we'll see, and we'll bring C on the other side and we'll rename it as B. Let's C is equal to minus B, let's assume. Then we'll call it as B and greater than 0. We can write it like this, same equation, no problem. Okay. Now when we have written it like this, then let's see, let's formalize this also. Okay. So my margin, I will say this is my positive class. So my margin is anything greater than +1, and for my decision boundary, I am saying it's greater than 0. But I do not want any point to be in the gutter also, or in the road also. Then what I will say? I will say the left side margin is if it is -1. How we'll write this equation? We'll write this equation that W dot product of X plus B, if it is less than -1, then it's a negative class, right? It is lying on the left side of the margin also. And if the dot product of W, which is perpendicular vector, with X, which is the observation, plus B is greater than 1, then it will land on a positive class side, right? It will land on this class. So now friends, you will ask me that why we are doing this -1 and +1, why not? Actually, it doesn't matter. Ultimately you will see that this +1 or -1 is just a number, and we want it to be equidistant. You can put it as like any constant, -k and +k also. It will not matter, and I will see you that how it will not matter, right, in just a minute. Okay, trust me for now that we are assuming -1 +1 so that they are equidistant. That's it, right? The actual number 1 doesn't matter that much. Okay, now if we have the points on these support vectors, right? If the points on the support vector, what will be the equation for that? If let's say we have 2 points, which is one x negative and x positive, and these are my support vectors. These are my support vectors. So what will my equation look like? On that point, on the margin itself, I can write it like Wx plus, this is my positive support vector, plus B is equal to 1, and W dot product minus support vector plus B will be equal to -1, correct? Because I was assuming that anything left to that, or the less than -1 is on the negative class, on the positive class. But what about support vector? This inequality will change to equality, correct? Okay, now let's do something else. Okay, now what we'll do is we will take the first equation. This is my first equation, this is my second equation. From first equation, what I will do, w dot x positive class is equal to 1 minus b, right? From my second equation, w dot x minus class will be equal to minus 1 minus b. Correct? No problem. Okay. Now let's see that what is my intention. My intention is to maximize this particular margin. And what is this particular margin? Let me try to draw it or erase it a little bit. Okay. Let me try to draw. Okay. So what it was there are two lines. Okay. So this is one, this is positive x negative and this is x positive, right? X negative and x positive. Okay. And this is my w. This is my w vector. Okay. Which is perpendicular. Now if you see, to calculate this particular width, what I need to do is I need to do x plus minus x negative vector. What I will do is I will subtract this vector into this and then take a projection on the perpendicular line, right? Then I will get this distance d, right? Whatever that distance d is. Correct or not, right? Let me make you understand one more time with a different color. Okay. So this was my negative support vector. This was my positive support vector. Correct? Now, if I have to get the distance d, the width of the road, what I will do? I will do x plus minus x minus, both vectors. Okay. And then I will do a dot product with w, right? Why will I do a dot product with w? Because this particular vector, which is x plus minus x minus, I want to take a projection on this, right? I want to take a projection on this w. And I have to divide it by w norm because I only want a unit vector. I need it for projection purpose, right? I do not actually need the length of w also to get multiplied, right? So this is what we are trying to get, right? This will be my width of the road, right? Correct? Now let's see. So my width of the road will be your over here will be, if I have to, again, if I have to subtract this, w dot x plus minus w dot x minus will be 1 minus b minus 1 minus b, which is equal to 2, right? Then what I need to do is over here is this particular w I can rewrite, I can take common. So w dot x plus minus x minus is equal to 2. And friends, now recall that what I wanted to get, I wanted to get x plus x minus w by w norm, right? Okay. So I will divide both the sides by w norm. So w by w norm x plus minus x minus, my support vector, 2 by w norm, right? Now this is my width of the road, right? And what it came to? It came to 2 by normal. So my width will be equal to, let me write it differently. Okay. So my width is equal to 2 by norm. And I have to maximize my width, right? That is my intention, that my width should be maximum possible, right? So what I will do is I have to do a maximization of width. I will represent it by width, which is maximization of 2 by norm w. Okay, but since we have to get our loss function, which is always we have to minimize, it will be the reverse of this. So we have to minimize norm of w by 2, right? Now friends, initially I was saying that this 1 doesn't matter. This 1 which you are saying, right, doesn't matter. Let's say if you would have taken k over here, right, k, what would have come? It would have just come 2k. That's it. right? It would have been a constant over here. And when we are doing a minimization problem, you know that the constant doesn't matter, right? What we need to minimize is the norm of W, right? And if we have to minimize this function, we might as well minimize the norm of the square, right? Minimize, right? Divided by 2, okay? And now why divided by 2 will come, because if we have to take the differential, then the max will become easy and it will get divisible by 2, right? So the loss function for maximal margin classifier is your norm of W squared divided by 2 if you have to minimize, and whatever value of W and B which you will get out of it will be your W and B which will have the maximum width of the road, right? Or the best fitting decision boundary, right? So my friend, this particular thing is clear, that how we arrived at this particular equation, the loss function, which is over here, right? Now let's move on to our slide. Okay, this I think we have already covered over here in great length. This again, I was seeing that the min of W and min of half W, or the norm of W square, right? And this is for the reason that the differential works, right? Now we have done this for the maximal margin classifier. Now what about your soft margin classifier, where we allowed some of the misclassification also to happen? For that, my friend, will be this equation. So the first part of the equation, if you see over here, is your what we have just proved. The second part of the equation is called L1 regularization. Why L1? So there are L1 regularization and L2 regularization, right? This is based on the distance, right? So this C particular term, right? The second term over here dictates how many misclassification you can do. The first term dictates how wide the road will be, right? So they are acting in opposite direction, right? If you increase the width, obviously your misclassifications will increase, okay? If you decrease the misclassification, the width of the road will increase, and that's why it's a regularization term. So the value of C which we'll be selecting, and we'll be doing that in our code example, is very, very important, okay? Now let's try to see that what this C intuitively means. C is a constant, it's a hyperparameter which needs to be tuned, right? If we select a large C, right? If we select a large C, what does it mean? It means that there are lesser classifications, misclassification which is happening. It also means a smaller margin, right? Less classification, a smaller margin, right? What will be the small c? A small c is the opposite of that. There will be larger margin separating hyperplane, but there will be more misclassification also. So it's another case of a bias variance trade-off. Large C means higher variance. What do you mean by higher variance? Higher variance or low bias means that the data, my model is fitting to the data more, right? And it is predicting very well. But will it be able to predict on the newer observations? No. Small c means low variance and higher bias, but better generalization. Low variance, that my data is not, my model is not fitting the present data or the observed data, but in case of future data or the future observations, it will have better predictive power. That is the meaning of a small c. So we cannot keep c too large or too small. It's a hyperparameter which needs to be tuned. Okay. Now let's see another example of what they mean by a small c or the large c. The middle line, the green line, right? It is doing a good job at the classification, right? This has a smaller c, right? A smaller c means large margin separating it and the hyperplane and more. But what it is doing, it is allowing a misclassification over here, right? More misclassification. But suppose if we draw a line like this, in that particular case, we are increasing the c. We are narrowing down the road. The road will be very narrow in case of this orange line, right? then it will be very narrow. So this is the case of a large C, but we are also reducing the misclassification because our roads are narrow, and I have tilted this my decision boundary over here. And by taking a large C, that means there are less chances of misclassification. So it's always a trade-off between bias and variance, the value of C which needs to be set. Okay. Let's see with another example. And in this example, if you take the value of C as 0.01, this is how it looks. Okay. A small C, more misclassification. If you increase the C tenfold, right, 0.10, this has shrink, right? This has shrink, less misclassification, but the smaller margin. We went to 1, another 10 times, right? Further shrank, right? Less misclassification. We 10 to 10, very, very less. Now, friends, do you think that this particular model or this particular model, which one is going to generalize well for the later cases? If there is one more new observation which comes on the left side, it will classify it as the red, but it may be green, right? But over here, the chance of generalization is much better. The predictive power is much better in this particular case. So C should not be too small, it should not be too high also, right? Okay. With this being said, I think we have come a long way. Now in the next video, I will stop it over here. In the next video, I'll deal with the our support vector machine, okay, and how we deal with the non-linear. Till now we have seen the data which can be linearly separated, right? We'll see how the data which are non-linearly separated, non-linearly separable, how we deal with that, and that comes as a support vector machine. We'll also see the code behind it, right? So with that being said, let me put a stop over here, and thank you for watching. And I do have a favor to ask you. If you have not subscribed my channel, please do that. It will mean a lot to me.